everyone. In this video, I'm going to present my project, a Ternary Neural Network Accelerator implemented on an FPGA for handwritten digit recognition. The core idea of this project is to design a dedicated hardware accelerator that can perform neural network inference efficiently without relying on a CPU or GPU. We achieve this by deploying the entire inference pipeline directly onto an FPGA. The key architectural decision in this project is the use of ternary weight quantization, where instead of storing full precision floating point numbers, all network weights are constrained to three discrete values -1, 0, and +1. This quantization eliminates the need for hardware multipliers entirely, significantly reducing resource utilization and increasing computational throughput on the FPGA. The result is a fully pipelined parallel inference engine capable of processing an entire MNIST digit image in just 160 clock cycles. The dataset we used is called MNIST, which is a collection of handwritten digit images, each of size 28 by 28 pixels. Each pixel has a value from 0 to 255 representing brightness. We converted these values to a range of -127 to +127, which is more suitable for hardware processing. The image here is the specific test image we used. It is the digit 5, and our goal is to make the FPGA correctly predict this. Now, let me explain the neural network we built. We have a single layer network whose input is 784 neurons, one for each pixel of the 28 by 28 image. These connect to the 10 output neurons, one for each digit from 0 to 9. The key innovation here is our custom layer called ternary dense. Instead of using normal floating point weights, it forces all weights to be either -1, 0, or +1. But here is the main challenge. If we directly train with these restricted weights, the model cannot learn properly because small gradient updates get lost. So we use a trick called STE. This is the straight through estimator technique. In this technique, we keep a full precision floating point copy of the weights called shadow weights just for training. During the forward pass, we snap them to ternary values, but during backpropagation, the gradients flow through the full precision copy. This way, the model learns properly while still using ternary weights for actual computation. So, now let's run our Python code. We train the model on MNIST images, as I have mentioned earlier, for 10 epochs using the Adam optimizer. So as you can see, our code has already started running, and the accuracy improves each epoch as the shadow weights gradually get pushed past the threshold into -1 or +1 territory. After training, we visualize what each neuron has learned. Let's wait till the codes get completely run. So here is our image. Each image here shows the weights of one neuron reshaped back to 28 by 28. The white regions are the +1 weights, the black regions are the -1, and gray is 0. These patterns represent what each neuron looks for in an input image. Finally, we extract the ternary weights and export them along with the test image into COE files, which is a special format that can be loaded directly into FPGA memory. So now comes the hardware side. We implemented this neural network in Verilog and applied it on FPGA. The top module connects everything together. The weights COE file is stored in a ROM, that is read-only memory, and the input image COE file is also stored in memory. Both are loaded into the FPGA at programming time. So every clock cycle, 5 pixels and their corresponding weights are fetched from memory simultaneously. We have 10 TMU cores, that is ternary multiply units, running in parallel, one for each digit neuron. Now let's move to the TMU core module. Each TMU core takes the same 5 pixels but uses different weights and computes the partial sum for its neuron. The beauty of ternary weights here is that there is no actual multiplication happening. If the weight is plus 1, we just pass the pixel as it is. If minus 1, we just negate it. And if 0, we skip it entirely. This makes the hardware extremely simple and efficient. Now let's go to the nanocontroller module. The nanocontroller is the brain of the system. It is a finite state machine with 4 states: idle, calculate, find maximum, and done. When the start button is pressed, it begins reading through all 157 memory lines, processing all 784 pixels in groups of 5. After all cycles are complete, each of the 10 neuron accumulators holds the total score for its digit. The controller then finds which neuron has the highest score, that is, the predicted digit. The result is displayed on the LEDs of the FPGA board. Now let's go to our simulation. So, in our simulation here, you can see done LED goes high after inference is complete and LED results show the value 5, which is exactly the correct answer for our test image. Now let's program our device. This is our reset button and this is our start button. This is done LED and these 4 are our output LEDs. As you can see, it is 0, 1, 0, 1, which is 5. To summarize, we successfully trained a ternary neural network on the MNIST dataset in Python, exported the weights and test image in a hardware compatible format, and implemented the entire inference pipeline on the HRTX 7 board using Verilog. The key highlights of this project are: first, ternary weights restrict all values to -1, 0 and +1, making hardware implementation extremely simple with no multipliers needed. Secondly, the 10 TMU cores run in parallel, processing all 10 neurons simultaneously every clock cycle. Thirdly, the entire inference for one image completes in just 160 clock cycles. This project demonstrates how neural network inference can be made hardware friendly and efficient, which is very relevant for edge AI applications where power and speed matter. Thank you for watching.